Shanam. My name is Akash Alawat, and today we are going to study about thermodynamics equilibrium and properties of system. Thermodynamic equilibrium. So, what is thermodynamic equilibrium? A system is said to be in thermodynamic equilibrium if it is in phase equilibrium, thermal equilibrium, mechanical equilibrium, and chemical equilibrium at same time. If any one of these equilibrium condition disturbed, then the system cannot comes under thermodynamic equilibrium. For having better understanding, let's understand all these four kind of equilibrium. First of all, we have thermal equilibrium. The system is said to be in thermal equilibrium if it has equality of temperature with surrounding. Let's say our room temperature is at 25 degrees Celsius. We are boiling water in a jar. Let's say the temperature of this water rise up to 45 degrees Celsius. Now stop providing heat to this water. After shutting down the heat, what we will observe after some time is that temperature of water from 45 degrees Celsius goes down to its room temperature. After some time, water will attain temperature of 25 degrees Celsius. Now, the condition for this system that establish is what we call thermal equilibrium. Now the system attains its condition where its temperature is equal to room temperature. We have one more good example to understand thermal equilibrium, and that is a dead body is always in thermal equilibrium. Let's understand this. Actually, normal human body temperature is approximately 37 degrees Celsius, whereas temperature of our surrounding keeps on changing. Sometimes it's cold and sometimes it's warm. Here in India, in winter season, temperature is generally around 6 to 7 degrees Celsius, and in summer it reach up to 44-45 degrees Celsius, which is normal. So we have lots of variation in temperature in our surrounding, but our body stays at around 37 degrees Celsius. This is because our metabolism is continuously running, converting calories into heat. Let us consider surrounding temperature is 25 degrees Celsius, but our body temperature is at 37 degrees Celsius. If a dead body is there, then you can check that temperature of the dead body is also 25 degrees Celsius, because metabolism of dead body shuts down and it will attain a temperature equivalent to surrounding. Now that condition, when body attain temperature equivalent to surrounding, is called thermal equilibrium. Now moving further, second one, we have phase equilibrium. When mass of each phase remain constant with time, then the system is in phase equilibrium. Let's understand it with an example. Consider a closed container which is partially filled with water. And here we have air. Now at starting, this container is not in phase equilibrium because here we have tendency of changing phase, that is liquid phase of water will evaporate and change into gaseous phase. Now here air have tendency to absorb water vapors. So from starting, air will absorb some water vapor, and after some time we'll see that this system attains its saturation limit. At saturation limit, air will stop absorbing water, or we can say evaporation of water will stop. After attaining that saturation limit, there is no tendency left for air to absorb water, or there is no tendency in this system to convert this liquid form of water into gaseous phase. At that saturation limit, we have fixed mass of water. Let's consider this to be ml, like mass of liquid, and we have fixed mass of air. We have fixed mass of water vapor. Let's consider it to be mg, mass of water vapor or gaseous form. Now in this system, tendency of conversion of phase is not there when it reaches its saturation limit. So after reaching its saturation limit, ml will be constant and mg will be constant. There will be no possibility of phase change here. From here we can conclude that now this system reaches its phase equilibrium. So next one we have chemical equilibrium. Generally in chemical reaction, on left side we write reactants, and when chemical reaction occur we get byproducts, and on right side we write the products we get after chemical reaction. So in chemical equilibrium is the state when both reactants and products are present in concentrations and have no further tendency to change with time, so that there is no observable change in properties of system. Generally it occurs when rate of forward reaction is equal to the rate of backward reaction. In simple language, we can also say that chemical reaction potential should not be present. At that condition, we can conclude that our system attains chemical equilibrium. Now moving on to next one, we have mechanical equilibrium. A system is in mechanical equilibrium when net forces acting on that system will be zero. It is basically equality of forces, nothing else. It can also be defined as the pressure acting at any point of the system does not change with time. We can also understand this with example of our solar system. Consider our solar system to be the system observable thermodynamic system. consider this to be sun, and we have all the 9 planets revolving around the sun. Now these all 9 planets are in mechanical equilibrium because gravitational forces acting from the sun, or these planets have its own gravitational forces. They are at equilibrium. They keep revolving around the sun with fixed revolution, fixed distance. The only case when their mechanical equilibrium is disturbed when some kind of asteroid or heavenly heavy body collide with these planets. In that case, their mechanical equilibrium may slightly be disturbed. But after that collision, they again attain their mechanical equilibrium. So this is the best example of mechanical equilibrium where gravitational forces are at equilibrium. For disturbing their equilibrium, we need a heavy amount of forces. Then only their equilibrium can be disturbed. So this is all about thermodynamic equilibrium. Whenever our body is in all those 4 equilibrium, that is phase equilibrium, chemical equilibrium, mechanical equilibrium, and thermal equilibrium, only then we'll consider our system to be in thermodynamic equilibrium. If any one of this equilibrium will disturb, then we can't consider our system to be thermodynamic equilibrium. Now moving on further, we have properties of system. Properties of system. Any characteristic of system we call as property of system. Now this property of system is classified into 2 categories. First one is intensive properties, and the second one is extensive properties. Intensive properties, also known as intrinsic properties, and extensive properties is also known as extrinsic properties. All those properties which are independent of mass, are termed as intensive properties, like temperature, pressure, these properties. How can relate this with mass? These are independent of mass, nothing to deal with mass here. So these all properties are intensive properties. Like we can consider a system. If its temperature is changing, does it affect its mass? Or if its temperature rising, decreasing, whatever is going on, it does not have any relation with mass. Change in temperature or change in mass will not affect its temperature. Likewise, pressure. So all those properties which are independent of mass are termed as intensive property. All the specific term, like specific enthalpy, specific volume, these all also comes under intensive properties. Specific itself is very important term in thermodynamics. We'll do a detailed discussion on this specific term when we'll study about entropy, enthalpy. In that lecture, we'll study specific term in detail. Now coming on to next, we have our extensive properties. All these extensive properties are dependent on mass of the system. Depends upon mass of the system. For example, we can say that volume is the property which depends upon mass of the system. Energy is dependent upon mass. Enthalpy also depends upon mass. Now, we have some important points to discuss with respect to properties. Right? Property of a system is defined at any particular instant. So it is also called as point function, or we can say it is a state function. Property does not depend upon the past history. Here, past history basically refers to the path that follows by a system. This path is generally the changes occurs in system with time. Okay, so we can also term properties are the exact differential. Like at any instant, say at t1, we have that's t1 considered to be the initial state of any system. We have its temperature at capital T1. T1 basically represents time, T1 time. Say we have capital T1 temperature, we have P1 pressure or V1 volume. Now let's consider system goes through certain changes, and after some time, small t, after some time at time t2, the system attains a condition where its temperature is T2, its pressure is P2, its volume here is V2. So now this T1, P1 and V1 itself define this system at this time T1, and this T2, P2, V2 depends the condition of the system at time T2. It has nothing to deal with the changes that comes inside the system with time t. So this is also, so therefore we can also say that these are exact differentials. So the properties have nothing to deal with path or the changes that comes in the system with time. They itself defined system at any particular instant. They itself define condition of the system at any particular instant. So it has nothing to deal with time or the path the system is flowing or the changes that are coming in the system with respect to time. One more thing to remember here is that work or heat is not the property of the system. Work and heat does not come under the property of the system because they are not defined for a particular instant. They are not a time function, they are path function. And they depend upon the past history, that is the path through which the system passes. Okay, so we can also consider, so therefore work and heat are inexact differentials.